Welcome to lesson number 11, Linear Functions and Geometry. The meaning of geometry in this lesson title should be taken in the classical sense. As you probably know, the meaning of geometry, just like the meaning of algebra, has changed and evolved through time. What we're going to do in this lesson is look at properties of geometric objects such as circles and polygons and discover some linear relationships within them, linear functions therefore. In some ways, what we're about to do is similar to the previous lesson of mathematical modeling. In other ways, it is quite different. Here are the similarities. We will investigate two situations. In the first, we will collect the data in class. In the second, we will shortcut the data collection, assuming that you will do it on your own. Some further similarities between math modeling and this lesson. 1, we will pose some questions. 2, we will find a linear function of the form f of x equals ax plus b, relating input and output variables. We still call this a model. And 3, we will use f of x to answer the questions. What is the difference between those investigations and the two in lesson 10? You will discover the difference. Hopefully, these two explorations will not only increase your knowledge of algebra, but will also increase your knowledge of geometry. Our first investigation. What is the meaning of pi? When I teach this lesson to whatever students, be they students, college students, high school students, or teachers, I ask the question, what is pi to you, before I do the exploration? And I say, take a moment and write it down, supposing you have some mathematical dictionary about to be published and you were asked for the definition. Well, very commonly what I get is pi is 3.14. So then I say, fine, that's a numerical value. But take that further. What is the meaning of the value 3.14, or even a better approximation? So I'd like you to stop the tape for a moment, take a moment, jot down your definition just for yourself. What do you think the meaning of that number is? And then find out how close you were to the right answer. Compare your definition that no one will know except you and what we will find in this lesson. So to investigate the meaning of pi, let's go to our first exploration in our mathematics laboratory. Here we have 5 circles of different sizes. Under the column D, we're going to measure the diameters of these circles in centimeters. The first circle has a diameter of 4.1 already pre-measured, so we can remove that one. The circumference will be under the second column. That first little circle has a circumference of 13 centimeters. The third column is a surprise. So let's take the second one. The diameter is about 7.5. And the circumference is approximately 23.4. Let's do one more. Let's take the third circle and measure the diameter. That's about 9 1/4 or 9.25 centimeters. And the circumference, which is the walk around the circle, is about 29, almost 29.5, but it looks like 29.4. That leaves us with 2 more. In the interest of time, I've already pre-measured them. The fourth one has a diameter of 11.75 and its circumference is 37.2. And the last one has a diameter of 15.2 centimeters with a circumference of 47.5. Now, the third column, I would like to compute the quotient or the ratio of C divided by D in each of these cases. If I take the first two, 13 divided by 4.1, if you use your calculator or do that by hand, I've already computed it, so I know, is 3.1707. I, of course, used my calculator for this. 23.4 divided by 7.5 is 3.12. 29.4 divided by 9.25 is 3.1783. 37.2 divided by 11.75 is 3.1659. And the last quotient, or ratio, 47.5 divided by 15.2 is 3.125. Now, if you take these numbers, 1, 2, 3, 4, 5, and you take their average, because there's always human error along the way, the average of these 5 numbers is 3.1519. But what is that number? It's very close to pi. Pi is 3.14 ... So what have we found? That the ratio of C to D of any circle is pi. That means that if I take the circumference, divide by the diameter fits a little more than 3 times in the circumference of the circle. Let's express this as a linear relationship. We found that C divided by D equals a number which we found to be 3.1519. But we know that in theory, that's the number pi. We were relatively close, actually very, very close. But if I now cross multiply, C times 1 is C equals pi times D. But this is a simple linear relationship. C is the output variable, pi is a number, that's the A, and D is the input variable, or X. This is the form Y equals AX plus B, where B happens to be 0 in this case, and A is the slope. I have put those values into the calculator, the X list and the Y list, the C values and the D values. Actually, the diameter is X and the circumference is Y. And I'd like to plot those points for you to see that it's a linear relationship. Under L1, we have the diameters, 1, 2, 3, 4, 5 of them. And under L2, we have the corresponding circumferences that we measured. L1 and 2, we need to plot those. So we go to stat plot 1, so we can plot L1 versus L2. Let's turn that on. Now we go to zoom. We've visited this several times. Zoom stat, and there are our points. Now this is the relationship we found with a slope of 3.1519. But if I go to Y and I write the equation pi times D using the pi of my calculator, and I have pi in here, there is pi, and D would be the X. If I now graph that on top, well, it looks like a very good fit. Why? Because pi and the number I found differ by 1/100th, so it looks perfect. Let's turn those plots off, meaning let's delete those particular points and look at the entire graph. Plots off is number 4. Now we have the continuous line. We could also zoom out a bit, so if I trace and I go to zoom, zooming out will allow me to see more of the graph. And there we have it. Suppose we wanted to answer the question. If I had a diameter of 30 or 20. What would the circumference be? Let's pick 20. So a diameter of 20 means I need to find x equals 20. Oh, sorry, I have to trace. Sorry, let's do that again. If I trace and I go to 20, there I am approximately. At 20, I would have a circumference of about 64. If I wanted the exact value, I could go to table set that equal to 20, and then look at my table, and I have the exact value of the circumference. Staying with the table, suppose I had a circumference of 80. What would the diameter be? Well, now I go down the circumference, I look for 80, and it's coming. And there it is, approximately. My diameter would be about 25.5. So I could go up and down these columns or along the graph and read at any point along the way, the x-coordinate would be the diameter, and the y-coordinate would be the circumference. And what is the relationship? This number is pi times this number, or this number fits pi times into that number. One last comment, what happens at the origin? Well, the line goes through 0. We could see that if we go to the table and set it equal to 0, and let's let 0.1 be the increment value. Let's go to table now, and there we have x equals 0 corresponds to y equals 0, which means that this line goes through 0, 0, which is the origin. And that's logical, because if I have a diameter that is 0, I'll have a circumference that is 0, because in fact I have no circle at all. It's a point, it's a non-existent circle. Let us recap what we have learned. We collected data, we understood the data, we organized it, represented it, and analyzed it. We then devised a linear model. We found f of x, or y, equals ax plus b, where y was the circumference, a was the value that was a little bigger than 3. We call that 3 plus. We actually found 3.1519, and x was the diameter d, and b was 0. But, and here is the difference between our investigation and the ones we did in mathematical modeling. There exists an exact equation, c equals pi d, which is the same thing as saying c over d equals pi. So while we found a model y equals 3.1519x, which was very close and a very good model, there in fact existed an ideal perfect model, and that is y equals pi x, or c equals pi d. That's the difference between what we did today and the problems we did in the math modeling class, when we looked at those blots of ink or when we looked at those used cars. We came up with very good models, but they didn't exist an actual perfect ideal model. Here it does, because it's inherent in the property of a circle. Pi is the ratio of the circumference to the diameter of any and all circles. So to leave you with a visual representation of what we found, the meaning of c over d equals pi can be represented by these two lines you see. C is the circumference stretched out like a string or a line segment, and D would fit 3 times inside of C with a little bit left over, and that's the 0.14 ... The approximate value of pi is 3.141592654, and so on. A little story about pi before we go on to the next investigation. The investigation into the meaning of pi has fascinated mathematicians for over 3,000 years. The Egyptians back in 1700 BC used an amazingly close number, 3.16. Archimedes of Syracuse in the 3rd century BC began the formal investigation into the meaning and value of pi with his very famous treatise called Measurement of a Circle. In the 5th century AD, the Chinese used a value where 6 digits beyond the decimal point were correct compared to what we know today. 1,200 years after that, in the 17th century, pi was computed with infinite series. You'll learn about that in your more advanced math classes. In the 19th century, some amazing computations were achieved by people who spent the time doing it by hand. There's one by William Shanks, a very famous one. He computed pi up to 707 places beyond the decimal point. And that was in 1873. And it was found out in 1948, when the first computer came out, that he had an error in the 528th digit. And he spent 15 years of his life doing that, if you can believe that. In 1949, the ENIAC computer computed pi to 2,037 places beyond the decimal point. In 1959, it went up to 16,000 places. And in the late 80s, with the supercomputers, they were able to print out pi with over 500 million digits beyond the decimal point. So this is a testimony of a 3,600-year journey and triumph of the mind of man. Now we're ready for investigation number 2. This time we're going to explore the relationship between the number of sides in the polygon. Here we have a 3-sided polygon called a triangle. Here we have a 4-sided polygon called a quadrilateral. Then we'll move on to pentagons and hexagons and heptagons. In each case, I'd like to compute the sum of the angles of each polygon. This is something that you could do by using a protractor and adding up after you've measured those 3 angles. Then you'd use the protractor and add up these angles. But we're going to assume that you've done that, and we're going to look at it from another point of view. And here we go. This experiment is based, theoretically, on a property of the triangle. If we knew how to compute the sum of these 3 angles that I have marked, then we could find a relationship for larger polygons. And since this is not a geometry class, I'm going to give you a proof of the sum of these 3 angles for any triangle, what I call a proof without words, or a visual proof. And here we go. If I bring this down and I fold it at a line that's parallel to the base, and then I bring this one in, and then I bring this one in, and I fold it like an envelope, I've shown that the sum of those 3 angles of the triangle gives me a straight angle. But we know that the straight angle is 180 degrees. So that's a really fun way of showing that the sum of the 3 angles in a triangle adds up to a straight angle, or 180 degrees. So keep that in mind. So we can put 180 degrees. That's the symbol degrees. If I go to the quadrilateral and think of it as 2 triangles, I connect 2 opposite vertices with a line. I have 1 triangle and 2 triangles, so the sum of all those angles would be 2 times 180, but that's 360. Let's go to a pentagon now. Here's a 5-sided figure, as you see, 1, 2, 3, 4, 5, and I purposely took non-regular ones, just arbitrary polygons, and I divide this one into 1, 2, 3 triangles. So I have 180, 1, 2, 3 times. I think you see a pattern. Let's go to a hexagon. 1, 2, 3, 4, 5, 6 sides. If I connect any one of the vertices to the other 3 that are not adjacent, I form 4 triangles. Each of these 4 triangles has 180 degrees, so that's 4 times 180. And for our last example, let's go to a heptagon. Here's a 7-sided, 1, 2, 3, 4, 5, 6, 7. I connect one vertex right here to 5 vertices because you cannot connect it to the adjacent ones. That wouldn't form a triangle. And I have 1, 2, 3, 4, and 5. So my total is 5 times 180. Again, if you had done this by hand, you wouldn't get the exact numbers, but you would get a model, and then you would compare it with this relationship, which is the exact ideal relationship. Let us plot these points in our calculator using the input variables to be the side number, or number of sides rather, and the output variable to be the sum of the angles in the triangle. I've already keyed in these values, so let's look at our lists. For a polygon with 3 sides, we have 180 degrees. That's a triangle. For a quadrilateral, we have 2 times 180, or 360. For a pentagon, 3 times 180, or 540. Hexagon, 4 times 180, or 720. And 7 sides, we have 5 times 180, which is 900. Let's plot these points. We have L1 and L2, so we need to go to stat plot 1 and graph L2 versus L1. So let's turn that on. Go to zoom, zoom stat again, number 9, and there are the points. Since we computed this using the property of a triangle, we know that these are exactly correct. If we were to trace them, there's the triangle, there's the quadrilateral, there's the pentagon, the hexagon, and the heptagon. Let's find the equation of this line. We go to stat, calc. We want a linear regression, a line that will be the best fit line, the line that the calculator will provide us with. So we select linear regression, and the lists were L1 and L2, so we have L1, comma, L2. And there is the perfect line with A, the slope is 180. Well, we knew that because the increment along the Y column or output column kept changing by 180. There is the B value, or the y-intercept, and a regression of 1 means we have a perfect line. And indeed, we do because we computed it using the property of a triangle. Let's graph this line. Y equals 180x minus 360. That's what we were just told. And let's graph it on top of those points. We now want to see more of this line, so we'll zoom out and we'll delete these points. So let's go to stat plot, turn the plots off, and we want to zoom out. So let's go to zoom down to 3, and there is the whole picture. We have the y-intercept, which we saw was negative 360. That's what the calculator gave us, so that's about right. And let's say now that we would use this line to answer the following question. Suppose our polygon had 1,800 degrees. What would it be? So we would go to 1,800. It's about there. Now let's see what we have here. At 1790, we have 11.9 sides. Of course, that's absurd, right? Because the sides have to be whole numbers. If I now go above 1800, I have 12.1 sides. So the suspected value is a 12-sided polygon. Let's go to table set and set 11 to be the number of sides. Let's increase by 1 and see what the table tells us. 11 sides gives a total of 1620 degrees, and indeed it was a 12-sided polygon that gave us a total of 1800 degrees, the sum of all 12 angles. We call that a dodecagon. Another question we could ask would be, instead of giving the degrees and finding the side, remember the degrees are measured here, the side is measured here. Suppose we had a 9-sided figure, a nonagon. So we would look for x equals 9, about there. So when x is 8.88, which is again absurd, we only want whole numbers here, we have about 1238 degrees, and when we have 9.08, we have 1275 degrees. So the answer is between those two numbers. Again, let's go to the table. Let's set that equal to 9, and if we look at the table, we have our exact value, a nonagon, 1260 degrees. I'd like to show you that you can find the answer to any of those questions by using symbol manipulation, doing the equation by hand. Let's look at the equation again. This is the equation that the calculator provided us with. The slope was 180 and the y-intercept was negative 360. X is the number of sides in the polygon, y is the sum of the angles. If I were to ask you, find the sum of the angles for a polygon that has 15 sides, you would plug in 15 for x and find y. That's easy. What about the other way around? Suppose we tried to solve what we did on the calculator. We said that the sum of the angles was 1800. It was just a value I chose. And we wanted to find the number of sides. That means we're looking for x. So we're really solving an equation here for x. Well, we know how to do that. If we want to isolate x, we add 360 to both sides. We get 2160 equals 180x. This gives me 0. But I want 1x, not 180x, so I divide by 180. Divide by 180, and if I think about it, or do it by hand, or mentally, or using a calculator, 216 divided by 18 gives me 12. So that's x equals 12. And that's how you would solve for any number. Consequently, if the sum of the angles is 1800 degrees, the number of sides is 12, and we have a dodecagon. So you see, you can compute this by hand or using the calculator, always both ways. Let us recap what we found in investigation number 2. We dealt with polygons, and we found a linear relationship of the form f of x equals y equals ax plus b, where y is the sum of the interior angles of the polygon, and a is 180, that was the slope, and x is the number of sides, and b was negative 360. If we write that with capital A for the sum of the angles, A for angles, and n for the number of sides, since it is a whole number, we have A equals 180n minus 360. This is a linear function or equation. It represents the relationship between the sum of the interior angles A, which is the output, and the number of sides n, which is the input for any polygon. Well, we have found two linear relationships of the form ax plus b. In the first case, b was 0. In the second case, b was negative 360. And these were linear relationships that we found where? In geometry. The first had to do with the relationship between diameter and circumference for any circle. The second had to do with number of sides and sum of interior angles of any polygon. Well, there are many such linear relationships in geometry and actually in every field. Why don't you go out and look for more? Do an experiment, calculate it, then use your computer and see if you can find new, additional, more linear functions.